Before we get started, a couple of reminders. We have lab 5, lab 4 tomorrow, and that is in the chemistry lab. So make sure you come to chemistry, make sure you bring your lab coat and your goggles so that we can do the lab there tomorrow, and it's on spectroscopy. So I'll see you tomorrow morning at 9 a.m. And lab 5 is actually based on this topic here. And we'll be doing that after the reading week. And so we'll talk about it a little bit later. So let's talk about hydraulics. Some quick definitions for you. First of all, we talked about hydrology already and the hydrologic cycle, which is the water cycle. So these things are all kind of somewhat related to hydraulics. Hydraulics is really the study of water movement, I guess at rest as well. So we're talking about things like pressure and water flow and things like that. And usually when we talk about hydraulics, we're talking about water going through pipes. And so this is relevant if you become a water operator or something at a water treatment plant. Hydraulics are super important. And so it's a short unit, and there's really 2 formulas to learn and a little bit of calculations to understand. So let's kind of get into this and talk about what we're looking at. Like I said, 2 things: hydrostatic pressure and continuity, which we'll get into. First thing to talk about, of course, is pressure. And let's talk a little bit about what pressure is. So you can see there's the definition. Pressure is the amount of force per unit area. So in the metric system, force is in newtons and area is in meters squared. So 1 Newton per meter squared is something called a Pascal. Now, a Pascal is actually a relatively small unit. So usually in the metric system, we're using kilopascals, which is of course 1,000 pascals. You may be familiar with the imperial units, which is pounds per square inch. And that's the conversion factor there. You can see both of those are actually on that particular gauge that's in there. So we are going to be using the metric system, but like anything, it's very easy to convert. You can find conversion factors on the internet. In fact, Google will convert things for you if you put that into the search bar, which is always very nice. One thing that you may be thinking in terms of, if you think about your high school chemistry, you're like, wait a second, what about atmospheres? Well, it turns out that pressure has many units for some reason. I'm not really sure what this is. I think it's just industry relevant. Some industries like to use 1 unit, some industries like to use another unit. So atmospheres, for example, are equivalent to the amount of pressure that the air would give you at exactly sea level. And so that's one way to look at it, and that's used in some circumstances. But the metric units that we're going to use are kilopascals, which are of course outlined here. There's also bars, millimeters mercury. All of these have historical reasons behind them. There's tons and tons of units, and people like to use different units in different places, but we will be sticking to kilopascals. So first thing I want to talk about is something called hydrostatic pressure. So static means not moving. So what does this mean? It means what is the pressure in water at a certain depth is really what we're looking at. And so if you take a look, this is 3 gauges, and you notice that gauge 1 is in very little water, gauge 2 is in a little bit of water, and gauge 3 is in a lot more water. So it turns out that the deeper you go, the more pressure is experienced. This probably makes sense because if you think about it, you have water on top of you. And the more water you have on top of you, the heavier it is and the more pressure you have. So there's a formula that relates to this. And we'll get to that in a moment. But basically, the metric unit we're using is, of course, meters. And so this is the conversion here, right? 1 meter of water is a pressure of 9.8 kilopascals. Under 2 meters of water is double that, so 19.6 kilopascals, and so on. So if you take a look at the bottom of the screen, there's some diagrams, and you can see we have some containers. And notice the volume of the container doesn't matter. All that matters is the depth. And often in many cases, we're calling the depth H. H for height of water. So we're going to be seeing that in our formula. So here's the formula here. Hold on a second. I thought I had the formula. There's the formula here. I'll come back to those slides in a second. And it's basically the pressure is 9.8 times the height, which is the number of meters. And so 1 meter of pressure is 9.8 kilopascals. 2 is 19.6, and so on. So we'll come back to that formula. We're gonna practice it a few times. Of course, if you're looking at the imperial American system where you want pounds per square inch, it's the same formula but a different conversion factor. So it's 0.43 times the height. The height is in feet, and that's going to give you a value in pounds per square inch. So let me just go back to some of these ones here. This diagram here shows you that it doesn't matter the shape or the volume or anything. All of these pressures here, all of them are exactly the same because they're all at the same depth. The water can be directly above you. It can be, there can be a pipe doing some sort of weird squiggly, and it only depends on the depth. And so that's why we have that equation, which is the pressure equals 9.8 times the depth, which is represented as an H for height. Here's the rules, right? Depends on the height. Increases with depth. I guess we said all that. It's the same point at all points at a given depth, and we'll see some examples of that. And that's kind of the points to make. So like I said, we'll try some practice problems here in a moment. So here's a good example showing water at different depths, right? So notice we have 2 tanks and they're connected by a pipe. Both tanks have the same amount of water in them. And so the pressure at A is equivalent to the pressure at E, and the pressure at B, C, and D are all identical as long as they are the same depth or height. All right, there's the formula. So let's try a couple of examples. So this one here, it says here we have a water tank and the depth is 3.5 meters. What is the pressure at the bottom of the tank? So we just grab our formula. Pressure equals 9.8 times height. We type in 3.5 meters, and 9.8 times 3.5 is 34.3 kilopascals. Okay, so that's a super easy one. The questions aren't quite always that simple, and most of these questions that I'll give you on a test are going to involve a diagram of some sort, so you may have some interpretation to do, and I'll show you an example or two in a moment. You can do the same thing with the American units. So you can see we have a water tank that's 25 feet, and notice in this case here, the gauge, so the water is this deep, the gauge is 15 feet from the bottom, right? So now we have to sort of think about what we have here, right? So here's our tank, right? And the tank is 25 feet. Okay, but the gauge is kind of up here somewhere, and it's 15 feet. So the gauge itself is really 25 minus 15 is 10 feet in the water. So to do that pressure or calculation, it's that formula, 0.43 times H. But we're going to do that subtraction. 25 minus 15 is 10 feet, and we're going to get 4.3 psi. So as I mentioned, I won't be asking you to do any imperial units. We're going to use all metric units for this on a test. And if you need to convert, you can convert very easily, like I said, in the real world, using all sorts of conversion measures. So here's another question, right? And so this is kind of more of a real world example, right? You have a water tank, and often the water tanks are up on a hill, or sometimes they're elevated on a structure of some sort. And then you have, something below the water tank. So below the water tank could be a warehouse, somebody's toilet, could just be a water hose, right? For fire suppression or something like that. So you can see here's the problem. It is 50 meters above the house, and but there's 4 meters of water in it. So how do we do that calculation? So very simple, 9.8 times height. The height is 50 plus 4 we add those two values together and then we multiply it by 9.8 and we get 529 kilopascals. So one note here, kilopascals, you're probably wondering the K. Should it be a big K or should it be a little k? And it turns out for metric, it doesn't matter. Both the big K and little k are acceptable as an abbreviation for kilo. Okay, so you could have kilograms with the big K, or you could have kilograms with the little k, and both are totally acceptable. Just in case you didn't know, that's not always the case with all the metric units. With K, for whatever reason, they decided both this is acceptable. Probably because they're very similar. And there's no other metric prefixes with a K on them as well. So here's another example here. And oops, there we go. This one here, again, another elevated water tank. And there is a little bit of piping involved. And so what we need to do is it's asking us to calculate the pressure at A, B, C, and D. So I just threw this down here to give me a little bit more space to write on the screen. Okay, so let's take a look. Here's A. Okay, so pressure at A. So it's always 9.8 times height. Okay, so 9.8 times, what is the height? So you can see our elevations are listed on the diagram. So the height, of course, is 100 minus 95 meters. And so that's 9.8 times 5. And grab my calculator here. 9.8 times 5. And that's 49 kilopascals. There we go. So that's A. So what about B, C, and D? So notice that B and C are at the same elevation. They're at an elevation of 70 meters. Okay, so B and C are going to be the same. So I'm going to write that right in my answer. So pressure at B is equal to pressure at C, and it's 9.8 times height. So that's 9.8, and the height in this case here, the total elevation of the water is 100 meters minus 70 meters. Okay, so that's 9.8 times 30 in this case. And okay, punch that in my calculator, 9.8 times 30, and that's 294 kilopascals. Okay, and one more, D. So we'll squeeze D in down here. Pressure at D, same formula, 9.8H, 9.8 times, in this case here, the elevation is listed on here as 55. So that's 100 minus 55 is my total elevation. And that's 9.8 times 45. Put that in my calculator. 9.8 times 45. I'm getting 441 kilopascals. Okay, so I'm hoping that is really straightforward. The main thing you need to do is read the question and make sure that you are accounting for any of the elevations. Because of course, these questions, that's exactly what they're like. They're going to show you some sort of real world problem. In the real world, there's a little bit of subtraction or addition that has to go in before you punch things into that final formula. Okay, I want to move on and kind of talk about this here. What happens when the water is no longer static? So that's worth talking about a little bit here. And that's going to be a couple slides for now. One sort of side note on this. Sometimes people don't even do the calculation. They might just talk about the pressure head instead. And the pressure head, really, they're just telling you what the depth is. And they're telling you, if you want to know the actual pressure, you can go and punch that in, multiply it by 9.8. So if you ever see that terminology, right, where somebody says there's 3 meters of pressure head, there's 24 feet of pressure head, they're just telling you how deep it is. That's it. And they're just telling you that that's how much pressure there's going to be. And if you really want to know, you can multiply it by the the correct number, which is 9.8 for metric. Here's a couple other sample calculations. We'll do them quickly. And just so we have some more examples, right? So sometimes you can see this one here is the opposite. So notice this, right? It's asking us to figure out the total depth of a tank. So let's draw out our little tank here, okay? So here's my tank, okay? And I got a pressure gauge that's 2 meters from the bottom. And what I'm trying to do is I'm trying to figure out the total depth of the tank, right? So that's 2 meters. Sorry about my sloppy writing here. Try to fix that. Okay, so we'll throw down our formula. Okay, so pressure is 9.8 times height. So in this case here, I have the final answer, which is 75. Okay, and so I'm going to manipulate my formula. So height is going to be 75 divided by 9.8. Okay, so let's figure what that is. So this question mark, by the way, is the height that I'm calculating right now, because that's where the pressure gauge is, of course. So 75 divided by 9.8 is going to be 7.65 meters. Okay, so the total depth in this case, of course, is that 7.65 meters plus where the gauge is at, so the 2 meters. So in this case here, my total depth of my tank is, I guess that's 9.65 meters. There we go. Now let me just flip back here for a second. I'm looking at my answer here. I must have, looks like I made an error there. I forgot to add the 2 meters onto my answer for this. But this is the correct answer. Like I said, sometimes you have an extra step to consider in these type of questions. Anyway, I'm hoping everyone's finding this quite straightforward. As usual with these questions, I do have sample questions that are posted on Moodle that you can work for studying purposes. And so do make sure you look at them before the next test, which is the Wednesday after the reading week. So here's another one here. It says we have a pressure gauge on an open tank of water and it's 0.5 meters from the bottom. Okay, so let's draw our little tank again. I always like to have diagrams because it helps me to think through the question. Okay, so here's my pressure gauge and it's 0.5 meters. Okay, and I want the total depth of the tank. So this is going to be the H that I'm calculating here because this is my pressure gauge. And it's asking for two things. What is the pressure head at that point? What is the total depth of the tank? So we'll pull out our handy dandy formula, 9.8 H. And we have the pressure, which is 88.2. Okay, so now we'll manipulate our formula. So H equals 88.2 divided by 90 or 9.8. Okay, 88.2 divided by 98 in my calculator. So it's telling me that this is 0.9 meters. Okay, so this is equal to the pressure head. Remember, the pressure head is just the depth, and this is the depth of the meter. And so that is the depth of the meter. The total depth, of course, is adding the two values. Total depth is 0.9 plus 0.5, and that is 1.4 meters. Okay, so like I said, I'm hoping that is pretty straightforward. For the most part, you're looking at just putting formulas into or numbers into a formula, and then crunching those numbers. Okay, I'm just going to go back here to the original question sheet, and I think I see what I did is that this here, it looks like it's supposed to be the answer here, and I didn't provide an answer for here. So I'll have to fix that in my next version of the course. But here are the solutions. And let's just, we'll make sure you use those as the actual solutions. Okay. That's kind of it for this for now. Like I said, on the next test, you're going to have one of these sample problems. There's going to be a diagram. It's going to have a water tank or some sort of system, a house or some piping. And like I said, you just need to figure out what the question is asking and use that very basic formula, 9.8 times H. And that formula is going to come back in with lab 5 that we're going to do after the reading week. So just stay tuned for that. Let's just talk a little bit about measuring water pressure. And there are different ways to do it. And I'm not sure if you've heard about some of these things in Neil's class about these piezometers. And let me just kind of show you what a piezometer is. A piezometer is basically where you stick a tube into a water supply. And if there's pressure in that water, water is going to come up that tube. And eventually at some point, so you've got the water pressure is kind of pushing up, and you've got gravity, which is pushing down. And that's basically it. So the water is going to rise in that tube to a certain point, and the pressure can be read off of the tube. This is useful for low pressure systems generally, and is kind of an old school way to do things. But again, I don't know if this is something you hear about in Neil's classes or not. Sometimes it's used to measure pressure in groundwater and things like that. And that's about all I know about these things. Maybe I should ask Neil about them a bit more sometime. Sometimes there's more pressure, and you can see like having a tube that's 15 meters long may not necessarily be that practical. So sometimes what is done is using a different system as well. Oh, here's another picture of another piezometer, and you can see basically it's the same idea. We're looking at water here in the middle. It's just a little bit more advanced than the diagram I showed you before. Sometimes we might use manometers. So manometer has mercury in it. So notice it says here that mercury is a lot heavier than water. And so the idea in this case is to see how much the mercury is pushed. And it's going to be pushed a lot less, and you're going to need a lot less tubing. So really the basic same idea. Most water pressure is read using these gauges, and there's a whole bunch of different types nowadays. You know, a lot of them are digital, of course, and whatnot. And usually the way these gauges work is there's some sort of spring in there, and as the spring gets flexed by the pressure, it turns into a reading on the gauge. So you know, this little needle is going to read, you know, up higher or higher depending on how much pressure is put on the actual spring. And the good news is nowadays, you know, most of them are having both metric and imperial units on them, and the digital ones are even more accurate than the old school ones. Okay, so that was part A. Part B is a little bit more tricky with the math. We want to talk about water flow in pipes, and we're using something called the continuity equation. So let's take a look at this equation here, and we're going to do a couple of sample problems, and that's kind of going to be most the end of the lecture. But these sample problems tend to be just a little bit more complex because often it's involving some conversions, okay? So let's take a look at what this whole thing means. So Q is the quantity of water, okay? So the quantity you can see is basically volume per second. And metric units, we want to use cubic meters, okay? And there's reasons for that, but we can use liters instead, but sometimes that just means we need to convert. Our metric time is seconds. We can use days or hours, and again, sometimes that involves some conversions. So this is the hard thing, is getting those conversions correct. V is velocity, so it's a little v. So when you write it, often you put a little wing on it like that to show that it's a small v, because remember that big V is volume, right? So we want to make sure we distinguish it from the little v, okay? And A is, of course, area, and most pipes are round, and so we got to remember one more formula. is the formula from grade 8, which is area is what? Pi r squared. Okay, so that's kind of it. Now all we have to do is put this all together and show you how to do one of these problems. So like I said, many different types of units. Cubic meters per second is often the preferable units, but we can use liters per second or megaliters per day. You're looking at like city systems. The city of Fort McMurray could be going through 50 megaliters in a day. And so sometimes that's a more useful unit. So we'll try one of these problems, and what I'll do is before the test, I'll do another one of these problems after reading as well. I know these ones are a little bit more difficult. So let's take a look at this one here. Okay, number one. Let me see here. I have a bunch of questions here. Yeah. So we'll do number one here first. Okay. So I always start off with these type of problems, and what I do is I write down the formula. Okay. That's where I always start. So Q equals VA. Okay. And so what do we have here? It says here how much water. So we're calculating Q. Okay. And we have a velocity. So that is our velocity. I can write that down there. Okay. And so what are we missing? We are missing our area. And we actually have a pipe diameter. So remember a pipe diameter, the diameter is the entire from one edge of the pipe to the other. And what we want is the radius. Okay, so my diameter is 10 centimeters. And 10 centimeters, of course, is 0.1 meters. So hopefully everyone knows that. There's 100 centimeters in a meter. If you don't know that, I can't teach that. That's something that you should know. So the radius is the diameter divided by 2. So that's 0.05 meters. And that's it. So this is a relatively easy one. The conversions are relatively straightforward. So I'm going to punch this into my formula, Q, and I can put all my units as well. And always put your units on these types of questions to make sure that you have everything there. So the velocity is 2.55 meters per second. Okay, and my my area, oh, I didn't calculate my area. We got to do that first. So area equals pi r squared. Okay, so let's punch that in. Area equals, so pi is 3.14. I actually have a pi button on my calculator I can use as well. And then my radius is 0.05 meters, and I'm going to square that. So I'm going to punch all that into my calculator here. So here goes 0.05 times 0.05 times 3.14159. Okay, so my area is 0.00785 meters squared. Okay, sorry for cramming things in here. I will put that down there. Times, so that's 7.85 times 10 to the minus 3 meters squared. Okay, so punch that in my calculator and multiply that by the velocity. And here is my answer. It is 0.020 meters cubed per second. So notice my units, right? I have meters and I have meters squared. So my final units are meters cubic meters per second. Okay, so always follow your units and make sure you have everything. This is going to be more important for question 2 and 3 and 4, where we have a little bit more work to do to get to our final answer. So let's take another look at another question, okay? And I'll show you how these are going to work. So take a look at this though. First of all, we have a 10 centimeter pipe, okay? And the water is flowing at this velocity. So question 2, so let me just write down that answer, or the answer is down here at the bottom, but the answer was 0.02 cubic meters per second, okay? So question 2, it says we have a larger pipe and the water is flowing slower. And you can probably see down at the bottom of the screen, yes, it's going to be the same, but it's worth doing this to make sure that that we have our answers right. So remember, Q is VA, okay? And I have my V and my A, is pi r squared. Okay, so that's 3.14. I'm going to skip the step where I'm calculating the radius in this case. I already know what the radius is because I have my diameter. My diameter is double the radius, so my radius is 10 centimeters. So in this case here, my radius is 0.10 meters, and we're going to square that. Okay, punch that into my calculator. So 0.1 times 0.1. Oops, try that again. My fat fingers aren't working properly today. Okay, I guess I could have done that one in my head. It's 0.0314. And don't forget your units. Okay, and so my Q is 6. Oh, and take a look at this. It's in centimeters per second. So I want to convert that to meters per second, right? So 0.64 meters per second times 0.0314 meters squared. And I'll just separate that out. Okay. Now punch that into my calculator, 0.64, and I get 0.020 cubic meters per second. Okay, so notice, like I said, we have a larger pipe. The water is going through a lot slower, but in terms of the math, it's actually the same amount of water, Q for quantity, right? Notice question 3, it says express my answer in liters per minute, okay? So what I'm going to do, there's different ways to do this, okay? And I can, so let me just rewrite this down here, 0.020 meters cubed per second. There are different ways to do this. You could convert the meters all to liters first, and then the seconds all to minutes. I'm going to do it kind of in one step here, and I'll show you how this works. Okay, so first let's think about our time. You probably know that 60 seconds is equal to 1 minute. So did you see how I did that? I did that in such a way that on the bottom I have seconds and on the top I have seconds, and so they both cancel out. So now by doing that math, it's going to convert it to per minutes instead of per seconds. So make sure you don't put it the other way. 1/60 is going to mess up your answer, okay? Because your units are not going to cancel out. So my second step, like I said, I'm sort of doing this all at once, is I'm converting cubic meters to liters. So that means I have to put liters on the top. And it turns out the conversion is that 1,000 liters is 1 cubic meter. Okay, so again, the math, right? 0.02 times 60 times 1,000. And I get 1,205 liters per minute. Okay, slightly different than the answer I have at the bottom of the screen. Again, sometimes it has to do with rounding or what I'm actually using for pi. I use 3.14 versus 3.14159 and so on. Those kind of things will make a little bit of a difference in the end. But in terms of significant figures, the first 2 significant figures are all good. And that's not a big problem. Okay, one more question to try. And this is the one that is just a little bit more of a beast. And I'll show you why that is in a second here. So don't forget your formulas, right? Q equals VA. Your area is pi r squared. And that's going to help you to get through things. So one more, this one is asking us for the opposite, asking us for the size of the pipe. So we don't know the area yet. And we have, unfortunately, our units are megaliters per day. So that's kind of the first thing that we have to deal with, is convert those megaliters per day. So that's my Q. So Q equals 50 megaliters per day. That's big M in day. So I'm going to convert that to cubic meters per second. And like I did on the previous slide, I'm going to do this all kind of at once, sort of one step at a time, but it'll all be punched in the calculator at once. And this one we have to think about a little bit more. So I think what I'm going to do is start off with the liters, okay? So it turns out that a megaliter is 1,000,000 liters. Oops, that should be a 10. That's 10 to the 6 liters over 1 megaliter, okay? But we want cubic meters, okay? So so that's gonna cancel out my megaliters. And so now we want 1 cubic meter is 1,000 liters, okay? And so that's gonna cancel out my liters. So notice in this case here, the conversion from megaliters to cubic meters is 1,000. I could have done all that in one step, but I want to do 2 steps to show you what's going on. Now the time, I'm gonna go down here. And so 1 day is what, 24 hours? So I cancel out my days on the top and the bottom. 1 hour is of course 60 minutes. That cancels out my hours. And 1 minute is 60 seconds, and that cancels out my minutes. So now I have to punch all this into my calculator. And so basically that means I'm taking 50 and I'm multiplying it by 1,000,000 and I'm dividing it by 1,000. And then I'm dividing that answer by 24. And then, I hit multiply. Let's start at the beginning again. Hold on a second, there we go. And then I'm dividing that by 24. And then I'm dividing that by 60. And then I'm dividing that by 60 one more time. Okay, so my Q, I finally have my Q, which is 0.579, and the units, what is left over is cubic meters per second. Okay, so we're going to punch this into my continuity equation. Remember that equals VA, and we're going to solve for A. Okay, so my V is up here, 3 meters per second. So my A is going to be 0.579 meters cubed per second divided by my velocity, which is 3 meters per second. So notice in this case here, 2 of my meters are going to cancel out and my seconds are going to cancel out. And what I'm going to be left over with is my, 1 meter is canceled out. I'm going to end up with meters squared. So the area is 0.193 squared meters. Okay, just enough space to finish off this question over here in the corner. I'm going to make a box for us. So remember that area is pi r squared, okay? So that means r squared equals pi, or not pi, sorry, area divided by pi. Okay, so that means r squared. I'm going to take my area. I'm not going to punch in the numbers because I have it right here. And I'm just going to divide that directly by pi in my calculator and put down the value. So my r squared is 0.0614, and that's going to be meters squared. So then I got to find my square root button, which is on my calculator here somewhere. Oh, where is my square root? There it is. Okay, so my square root is my r, and my r is 0.248 meters. And a pipe diameter, which is what's asked for in the question, is 2 times that, right? So my diameter is 0.5, that's times 2, let me just, 0.496 meters. So that's basically 50 centimeters. Okay, so like I said, this question here is the hardest because of all those metric conversions. And I'm not going to do any more of these today, but what I will do is, when we come back and after the reading break, is I'll do another sample, one of these or 2, just to get you going. But do take a look at the problem questions. There will be definitely a question like this on the on test number 3 after the reading. All right, I don't see any questions there. I guess I'll just move on this. So a couple other things about this. The first thing that you may be wondering is, how big is a megaliter, right? So this is the pool at Mac Island, okay? And so if you take a look at this, I'm looking at the big pool over here, okay? The big pool. And it's 50 meters long and 25 meters in the depth, and then it's 2 meters deep. So if you do this math, right, 50 times 25 times 2 is 2,500 cubic meters, which is basically 2.5 million megaliters, or sorry, 2.5 megaliters. So that's how big a megaliter is, right? This small pool here, this pool here might be about 1 megaliter, just to give you an idea of how big a megaliter is. Okay. Sometimes that's something that people have a hard time conceptualizing. So I thought the swimming pool would be a good way to look at it. So there's a sample question. You can see I have a note there to skip it. We're going to try that again when we come back from the break. We'll come back to that one. So something else about the continuity equation that I will not ask you to do, but this is something that engineers definitely think about, is that sometimes you have a big pipe leading to a small pipe, or a small pipe leading to a big pipe, and things like that. And it turns out that the quantity of water going through those pipes is the same. And that will change things like the speed, it will change the pressure, and things like that. And so this is something that might go into calculations. And you could imagine it'd be pretty easy to do this kind of calculation. If Q in equals Q out, and you don't know what the final velocity is or something like that, you can calculate it. But I will not ask you to calculate that kind of thing. Similarity, you could have one big pipe leading to two small pipes, and the total amount of the total quantity of water is equal to the sum of the quantity of water of those two subpipes. Like I said, I won't be asking you these kind of questions, so I'm just going to move on that. So there are just a few other things to kind of consider in this unit. And like I said, I'm not going to get into all the particulars of these because these things are not going to ask you about. But in terms of when people are looking at designing these systems, they're looking at all sorts of variables, and there's some of them there. You've got the elevation, the pressure head, the velocity head, all those kind of things go into the engineering of the system. And another thing that goes into the engineering of the system is it turns out that there's friction in pipes. So when water flows through a pipe, when the water is in contact with the surface of the pipe, there is going to be friction, and that's going to slow down the water, and it's going to add more pressure to a system as well. So this is something we are going to address in lab 5 after the break, and you're going to see the effects of this kind of thing over what's going to happen with different types of pipes. You can imagine different types of piping systems too. Sometimes you have concrete pipes, sometimes you have plastic, sometimes you have metal, and there's going to be more or less friction with the different types of pipes as well. So back to this diagram here, where we have some gauges. You can see we have a gauge here at number 1, we have a gauge here at number 2. And remember, what we learned is that the pressure in the system is relevant to the amount of water, the height of the water, right? So pressure 1 is equivalent to the amount of pressure at number 2. And the question was, what happens when we open this valve? I guess I thought I had this slide a little earlier in the notes, but that's okay. So it turns out when we open this valve, there's friction. There's friction everywhere in the system, wherever the water is flowing. So it turns out that you can see here that the pressure at number 1 is bigger than the pressure at number 2. So all of these calculations, once you open a system and have flowing water, the calculations are going to start to change just due to the nature of what's in the system. Sometimes there's valves as well that can add pressure onto this. So this is kind of the message to know: once water is moving, that energy is lost due to friction. Okay, like I said, a couple other kind of footnotes on this unit. There are many things to consider, and again, these are things that usually are considered by the people designing the systems, engineers and people like that. You can see we've got things like pumps and valves and fittings and bends and elevation changes and things like that. And just let me take a look at these notes here. There's some of these systems here are open, right? So you got a stream or a ditch, and some pipes are not open. And so there's all sorts of variables to consider. We're not going to get into all of those, but they're just kind of here in the notes to consider. And a lot of these nowadays are monitored by computers. And this is more likely what you will be dealing with, not designing the system, but dealing with the system. So it's a good idea to be comfortable a little bit with the units and comfortable with the ideas around pressure and flow and things like that. And I think that's actually it. So that's it for this topic, and I'll see everybody tomorrow in the chemistry lab, and hopefully everyone has a great break as well once we get to that. So I'll see you tomorrow.